Okay, so today we're going to talk about generator identification for linear SDEs with additive and multiplicative noise. This is a NeurIPS paper from this past year that builds on the work of Sokol and Hansen that Pardis presented 2 weeks ago. They proved, so the Sokol and Hansen proved that under appropriate conditions, the post-intervention distribution can be identified from the generator. And they also show in different examples and arguments that the generator is identifiable from the observational distribution, but they don't really make it explicit anywhere in their paper. So in this paper that we're presenting today, they make explicit sufficient and necessary conditions under which the generator can be identified from the observational distribution. So if we have time series observations of some continuous process, it's with some like noise, it's often nice to represent it with a stochastic differential equation. In this first equation here, we have dxt is equal to some drift term plus some noise term. And you can also express the same equation 0 in block form, where this axt is some row vector, and then the dzt is some column vector. So you can use whatever you prefer. Okay, so in this paper, they have two models, one with additive noise and one with multiplicative noise. So the additive noise one is up above here. And in this case, you can have kind of a nice explicit solution using integrating factor, where the solution is given by xt equals e to the at x naught plus the integral of e a t minus s g dw s. So this this w is the Brownian motion, and G is some matrix, and A is also a matrix. Yes, I can. Okay, so some practical examples of this additive noise model includes the Ornstein-Uhlenbeck process, which is the simplest case of SDEs, and it's often used for financial modeling and evolutionary biology. The next case we have is the multiplicative noise case, where now we have basically the same drift term plus a noise term where you have sum of linear functions times the process itself, xt, times the differential of the Brownian motion term. In general, we can't really get a explicit solution for this, but if we're only using one dimension, we can. It's just geometric Brownian motion given by the solution. And some practical examples of this include processes where you would expect that the noise grows with the magnitude of the process. So something like population growth or stream flow could be examples of this.
Okay, now that we've kind of defined the setup a little bit, want to talk a bit more explicitly about the causal setting. So there's a few different important concepts, and hopefully we can try to clarify these. So as Joe mentioned, we have an SDE, and there is a diffusion term, this one, and a drift term. And basically, the strongest thing that you can learn about the SDE, or you haven't melted something?
Well,
the strongest thing you can learn about the SDE is therefore knowing the parameters themselves. Because if you get the parameters themselves, you can characterize the entire equation. So yeah, you have the drift and diffusion, and it's standard to assume they're Lipschitz, otherwise it doesn't really make sense. You won't get existence uniqueness of solutions. One thing I do want to note is that in the model that we were introduced over here, the drift and diffusion terms only depend on the value of the process at the current time point. So like the most recent value. And I mean, a lot of us are currently looking into generalizing this, and you can certainly do that. It'll still be coherent. You could consider some, some lag terms. So consider like basically a history or a partial history. And you could also consider just dependence on time value itself.
Maybe we should clarify that that's not actually in the paper, but that's, our extra thoughts about it.
Yeah, the paper considers just the one where it's time value dependent. Okay, the strongest possible thing you can get is getting these parameters. Why? Because if you know the parameters, you can get a lot of things. For one, it can give you a theoretical characterization of the observational distribution. You could do that using stochastic integration. So if you know the parameters, then, okay, this is in block form. You could just integrate the SDE and then characterize the distribution of your solutions. So that's a nice property. And the observational distribution is pretty much what we'll be working with in practice, because when you're actually observing data, if you have enough samples of different time series that you're observing, you can approximate this empirically. So for example, if you're in a lab and you observe different time processes of, I don't know, some organisms growing or whatever it is that you're observing that are like IID, then you could approximate this just from your observations. So this is weaker, and you can obtain this theoretically from the SD parameters. A similar distribution you could obtain, which we saw in a previous paper from Sokol and Hansen, is the notion of a post-intervention distribution, which is very similar. You define it just by integrating, but the difference is we intervene by fixing the value of one of the causal parameters and seeing what the dynamics of the new system will be. And this is, a kind of intrinsic definition of causality, which is why I would be interested. So specifically, if you intervene on the Lth causal variable, then by setting to some Lipschitz function of it, then you'll have new dynamics governing the system, and it'll be of interest to know kind of how this new system evolves. So the only difference between the post-intervention distribution and the observational distribution is that we have basically one less variable to look at, and consequently, the way that the evolution works will be shifted because of the intervention. All of the time evolutions will be shifted. This has a lot of practical examples. One of them is like gene knockout. So for example, if you want to see how you can promote the growth of some organism like yeast, question could be like, which genes do you try to eliminate so that it grows the fastest? So it's a practical example. And again, this is something that you can obtain if you have the SDE parameters. The last thing that the SDE parameters allow you to get through some other parameters is the generator. And I'll explain this more in depth in the next slide. But essentially, the generator of a process explains how the process evolves in time and how functions of the process evolve in time. And it can be identified if you have an SDE of the form with a drift function and a diffusion function. It's not identified exactly by these terms because the diffusion function, because of the way variance or covariance scales, you can only identify up to sigma transpose, not sigma. So as long as like the gram matrix is the same for two diffusion functions, you'll get the same generator. And this will also be made explicitly clear by definition. But the generator will allow us to characterize a lot of other things. And but in particular, you will be able to always get it from the parameters because you can always just create these guys. The main task because this paper is generator identification, is to try to get the generator from the observational distribution, because this is the weaker one. Observational distribution is what you will actually see in practice empirically, as long as you have either multiple samples of the same time series, or if you have an ergodic process, because ensemble average would be equal to the time series average if you have sufficient observations of a single process. So if you have observational process distribution, the main question that this paper tries to address is, how can we characterize the generator?
Sorry. Quick question. I thought the generator was just the parameters.
The generator basically is the parameters. It's B and sigma transpose. It's not. Yeah, okay. Maybe I'll explain that now. It's probably the best time. The generator explicitly defined is like this. So it acts on functions. So it's a functional. And yeah, it's specifically, you have to have like somewhat regular functions that have, I think, yeah, it's bounded second derivatives. So you can see it's a kind of a sort of like a derivative of the process itself. So I think this is the definition that's maybe most concise, is given that the process starts at some initial value, X, it's the change in expectation of the process when you get very close to the initial starting point. And you can characterize this explicitly if you have an SDE of the form that we started off with. So 0 is the one where you have a drift term and a diffusion term that only depend on the fixed value, like the most recent value. You can compute this explicitly just by using stochastic differentiation. So for those of us that are in Miranda's stochastics course, it's just an application of Ito's formula. You can recognize this like 1/2 second derivative term. This is from Ito's formula. And in particular, you see why the generator from this is related to the parameters of the SDE. Because the first term only depends on the drift, and the second term only depends on not the diffusion, but the Gram matrix of the diffusion. So this is why the generator is essentially the parameters up to the Gram matrix of the diffusion. So this is why the parameters will give you the generator through generate parameters, but there's just a very slight distinction just because of how covariance scales. So the task in this paper is, how can you get from observational distribution to the generator? And equivalently, because the generator is defined by its parameters, how can you recover B and sigma transpose? Explicitly, they look at the two forms that Joe described. So we have additive. Yeah.
Can you show the data again? There was a I sub t, like X sub with the subscript down.
What just happened?
So those were the dimensions, but do you also have like many observations of the time course?
Yeah.
Distributional distribution on the left?
You like this one here?
Yeah, so that's just one random variable for each I and t, and then, so for I is in its dimensions, right?
Yeah, so
And do you have
there's
multiple versions of that as well?
you would have to have multiple versions in order to actually approximate the distribution, or you have a single one and it's ergodic, because then yeah, it's equivalent. But yeah, we'll see in the experiments that you assume, I think at least 5. Yeah, you assume at least 5 different observations of the entire process, which is d-dimensional. I is just one component.
It must be something like in the limit of infinite many, you would converge.
Yeah, you would converge to the distribution.
Like 5 is sufficient to exactly.
Yeah, I mean, you'll have some error in all of them, but yeah, I mean, I'll leave the experiment for a bit later, but yeah, in practice, you will need multiple copies in order to approximate the actual distribution. So yeah, so that's the data that you have. So in the setting that you have this kind of data, the question is, and I'll get to motivation in a little bit, the question that the paper interests or is interested in is how can you get the generator? And this is something that's like teased a bit in the previous paper by Sokol and Hansen, but yeah, it's not made explicitly clear. For the way to get here is, so the generator, once again, is defined by the drift and the gram matrix of the diffusion. And in the case of additive noise, well, what's the drift? The drift is going to just be, oh wait, I think this is wrong. It's linear, so there's no X. Okay, we'll leave that later, but the drift is just A, and the diffusion is also linear in the case of additive noise. So we need to identify A and GG transpose. For the case of multiplicative noise, it's a little more complicated. We also have just A here, it's a typo, there's no X. And we want to identify the gram matrix of the diffusion, where in this case, because multiplicative, you have the X involved. So we need to recover these in the setting of this paper. And you'll have two different theorems. 3.4 is for the additive one. You recover these and therefore get the generator from that. 3.5 multiplicative, you have to get these ones. Okay, but why do we care? Like,
I think because it's, yeah, B of X
Yeah,
should be
B of
A.
X is a linear function of X.
If it's just B.
oh, you're right. Yeah. Okay, yeah, that is fine. I bet. So yeah, we still need to recover these parameters from the observational data, but why do we care? The reason why we care is because of the previous paper where they showed, sorry, this is probably clunkier than I would have liked. The previous paper showed that if you have the generator, and this is in block form. So if you have a stochastic process in block form and you have the driving noise be a Levy process, and what Levy process means is just a generalization of Brownian motion, essentially, then you will be able to identify the post-intervention distribution, which is the one, for example, the gene knockout, so that the new dynamics, if you have the generator. And because both the multiplicative noise model and the additive noise model both follow this, because they're just using Brownian motion, that means that if you get the generator, then you get the post-intervention distribution. So in sum, the big picture, which again, I apologize, is probably a little too small to see super clearly. By contributing this, sorry, this question, yeah.
Yeah, I have a question. So, two questions actually. So for the observational data, again, are you observing this like for all uncountably many t times? Or is there some finite
You can have,
set of times?
yeah, you know, finite time. There's, yeah, you don't need.
In the experiments, it's equally spaced and finite, so.
Yeah.
But imagine if you have some very fine grid of times, then can't you just get, B of X regardless of whether or not it's linear or not? Can't you just take the expectation, sort of like in the definition of the generator, you can just take observations at some time t and some time s closely separated and just
Mhm.
you compute the sample expectation just from a bunch of observational data. Like if you have a bunch of samples of xt dimension I, and then x like time t plus delta t dimension I, and then just take the difference of those, and that should basically be b of x. Because the way that the SD is set up, that it's that plus some noise, and then the noise will have mean zero.
Mhm.
Right, so you can just take expectation, just that empirical sample average. Right?
Yeah.
Yeah.
Bunch of those.
Yeah, I think,
Unfortunately, it doesn't work in all cases though, so they'll show cases where like you can't just. There's no way of computing the generator from the observational distribution.
Oh, interesting.
yeah. No, but yeah, that,
Cases that are not.
Yeah, so
no, it's
we'll
still,
get to it later, but it's
Yeah.
probability 1 that you can estimate it, but there are certain cases where you can't.
it's rank conditions basically on the matrices that, the coefficients in front of the DT and the DWT. Like you need the diffusion drift terms to be well behaved. You get that with probability 1, but yeah. I think for the most part, your method, like the empirical method, would work for recovering the drift.
And is it because we're just having all these trajectories start from some common point? Because if they started from uniform across the whole space, if you could have if it was a compact space, you can find uniform distribution, and then you take some initial point uniform, And then you just have a trajectory, and then you should be able to just take expectation. So is the difficulty that there's some singular initial point, or what's the key? Maybe I'm interrupting too much, but
No,
what's the key difficulty?
Key difficulty
And
in,
just computing that finite, like just the sample average of the, x at time t, x at time t plus delta t, take the difference, and that should just converge to be weekly as you get more data.
yeah,
I think they're proving that it's not difficult, basically, like,
yeah.
it's easy with probability one, so.
Yeah, at least in this setting. I mean, one problem could be that, I mean, it would depend on how much data you have, and your granularity. Like if your noise is really overpowering, then the expectation, yeah, you might not get great results, right? So that depends also, like it would converge theoretically. In practice, I don't know. Like if you have a certain SDE with like a big dependence on the noise, I don't know exactly the rate of convergence, like how many observations and what like
Right.
intervals you would need to achieve
they're
reasonable.
Just focused on identifiability, it doesn't matter what the rate is, we can be patient, wait till we have 10 trillion samples and then conversion.
Well, they said they have 5
Yeah, the 5 samples wasn't great, I'd say, but they go all the way to 100, and the error is going down reasonably fast, but that's at the end.
Yeah. I mean, ultimately, I think I do agree that the empirical method should probably do pretty well. And I think it's consistent with their result. That, they get it with probability one, as Joe mentioned. But yeah, so yeah, I guess to highlight the big picture, if we have the observational distribution, which again is multiple samples of the time series data, in practice at least, then the goal that they're after is to identify the generator, because a previous paper showed that if you have the generator, you can get the post-intervention distribution, and that's like a key notion in causality. So this allows you to jump straight from observational distribution to post-intervention. So the next part, I'll just be going through, I guess the main proofs for how they do this, and it's split in two because there's two different models. So okay, it's the right zoom to get here. So the first one, they need to add an assumption. They need to add assumption to be able to do the task, which I'll just remind you, is if you have two observational distributions that have the same distribution, you want to show that their generator parameters are the same. So you need B and B tilde, you need the drift terms to be exactly the same, but you're allowed some deviation in the diffusion as long as their Gram matrices are the same. So they want to show that. And they want to show this first for the additive noise model. To do that, they have, okay, honestly, I'm really not a fan of this notation, but hopefully I can clarify. They have to add a rank condition, which later they'll show this holds with probability one from random matrix theory. Okay, what does this mean? So first of all, what's H? H is GG transpose. It's like the Gram matrix of the diffusion. And what is this big matrix? Okay, first thing, the vertical bars are not absolute value. They're to differentiate between entries. And you can view this entire matrix, I call it M, as concatenated two other matrices. And you'll see the significance of these from the proof. There's going to be M1. You'll see that it's basically action with respect to X naught, the initial distribution. This represents an entire system of equations where you have, which has two kinds of equations in it. The first kind is M1, which depend on X naught, and you have increasing powers of A. The second one is going to be a bigger system where you have, again, increasing powers of A, but you use it applies for each column of the Gram matrix of the diffusion. So the first one is D by D, and the second one, you actually have D squared, different columns here. So that means the entire matrix here is D by D squared plus D. And their condition means that this has rank D. So, okay, that's just the statement of what their condition means. okay, why is this bold? Okay, so the key thing is that if you have the same distribution, maybe I'll actually start, yeah, I'll start with this one. You have to identify both parameters. The key thing is if you have the same distribution, you'll certainly have the same statistics. And what they'll be doing is there's gonna be like three main steps is because same distribution implies same statistics at each time and each increment, then what that means is you can create a bunch of systems of equations that relate the parameters across different, I guess, yeah, against different equations. And then the rank matrix is applied at the end so that you can invert and then show that the parameters actually have to be the same. The first case of identifying the diffusion, because this is an additive case, this is really easy because it's a constant matrix. You can get this directly from the definition of the generator. Because, okay, you have the same expectations at each time for two xt and xt tilde. And then if you just differentiate this guy and evaluate at 0, this is kind of this definition of the generator evaluated x naught. So you have that the generators for any function will be the same at the initial condition. And remember that the generator of this SDE has a specific form, which you saw before, where, you know, this is like the Ito contribution. And then you can pick any function you'd like. You can pick this one in particular, where, okay, if you have d different dimensions, you could pick, and you want to isolate I and j, you can just basically just do a parabola. And what this will cause is everything in the second sum will either be 1 or 0, and it'll only be 1 for the I and j terms. So if you only analyze these two, then you'll see that 1/2 of this is same as this. And then because H is a grand matrix, it's going to be symmetric. So this actually concludes right away that the first or the second parameter, I guess, the diffusion one will be the same if you have the same distribution. The second one is going to be more challenging, but we're going to use the same idea. You know that same distribution implies same statistics. One thing that we'll be using is that if xt is from the additive noise model, this is how the statistics evolve. This is just, it's well studied because it's a Gaussian process. The way that your statistics evolve is just, yeah, you start from your initial condition and then you do the AT, and then covariance evolves similarly. So they'll use these. These are going to be equal at each time and each time increment. And you'll...
Sorry to interrupt.
Yeah, it's okay.
I have a question on this initial condition.
Yeah.
I was trying to ask this earlier, but this x0, is this like a critical, it sounds like this is a critical component of their analysis, that all of these trajectories start at this fixed point, x0.
Yeah, you're right. Yeah.
And I guess that makes the identifiability problem harder, right? Because you have sort of less information because all your trajectories are starting from the same point.
You mean it's more restrictive?
Yeah, like it seems like it'd be easier to identify the generator if you started from multiple points.
Oh.
Right? Because you would have sort of more diversity in where your trajectories start from. Right? That seems pretty obvious, right? Because like otherwise it's just a subset of the you have all the trajectories starting from that point.
Yeah.
But then in the limit of infinite data, you also have all the trajectories starting from other points. So it's just more information. So is that like how much easier did that make their whole proofs, the fact that you have this x0?
Well, it does get used explicitly because it's always like, for example, if you look on this part, if you had different starting points, then the time evolutions will be different. Like,
but the law could be the same, so xt is equal to in distribution to xt, tilde or
yeah,
not,
yeah.
but if they had, starting points with the same distribution, they would still be equal in distribution.
Yeah, they would be. It would be.
So is the fact that it's like, is it the case that, it's sort of obviously easy to identify the dynamics of any SDE if you have enough sufficient diversity in the starting point. And this is sort of a technical question they had, where like, okay, can you identify the dynamics if you have this fixed starting point? Like, what's their obsession with this X0? Where does that come from? Like, why is this
Well, I think that's probably standard in,
for them to have a fixed starting
I
point?
think in your application, it's just.
It seems like yeah, I mean, like, I wonder if that's sort of, is that the key difficulty, is to show identifiability when you have this fixed starting point?
That's not the impression I got, but
Okay.
I don't have much experience like with yeah, different versus same starting points. But just, I don't know, looking at the
Maybe
proofs, they
saying
use it.
starting point.
Well, it's embedded in their definition. Like if you look at how they define identifiability, it's given that the processes have the same starting point.
Yeah, so I mean, maybe the question is then, if you didn't have the same starting point, is it sort of obvious to, maybe not to us, but to, to them, that it would be identifiable?
You have to ask
And then-
them. It's not obvious
yeah.
to me. But yeah, I don't know. But for, yeah,
Because this thing, like just to finish, like the last question I asked was like, okay, can't you just take this sample average? And get the drift and diffusion just from, well, at least just get the drift from that.
yeah.
And that is probably only the case if you have a diversity of starting points.
I think you might run into trouble, just estimating the drift, because,
If you only have a single starting point, you mean?
well, no, just in general, because, at least in some of my research, I found that like you kind of need to model the noise at the same time as you're estimating the drift, or else
The noise
your
is just
kind of
Gaussian,
variance
right?
explodes.
Or isn't the noise just like Gaussian?
Yeah, it's Brownian motion.
Yeah, but,
Mean zero, so you can just take expectation of the difference between xt and xt with delta t. And that should be the drift as long as you have, enough data.
It'll certainly be hard for multiplicative noise because,
Or multiple.
yeah, I mean, this is additive. So, I think your thing would,
I'm
Right.
doing that.
yeah. Yeah. But even then, if you have like big parameters in front of the Brownian motion, like you might need a lot of data to overcome it. I don't know. Yeah. It's
Sorry to you.
It's okay.
I just want to get this xt.
Yeah, that's fair. They just assume it, and I didn't really think about it. But if you do assume it, then you can show pretty much exactly what you need to. Basically, you'll get one set of equations by equating the expectations. So if you equate the evolution of the expectations, then you can also differentiate them, evaluate them at any point, like 0, and you'll get a new system. And what's nice about this is that it's related to A, which is what you're trying to recapture, because we already figured out that G and G transpose can be identified. So you can get this system, you can rewrite it, and this is exactly going to be the columns. These guys are the columns of M1. So that's the first part of the block matrix that they're assuming. So, no, wrong one. These guys. This comes from the system of equations generated from the expectations being the same. The other one's going to be coming from the covariances, which is why it's going to be like quadratic number of equations. So you get exactly these columns and these form your M1. You do the same thing for covariance. And again, these are well known, how they actually evolve. Again, you can differentiate them. Here you'll do kind of a double differentiation. And this one will now be in terms of H. And you could still write the action on A. So you get two kinds of systems of equations. And these are exactly the ones that form the big matrix, which they impose the rank condition on. And because, yeah, you have equality here, you can try to show that A is equal to A tilde. Then finally, you get the result because you have these two sets of equations, one from the expectations evolving, one from the covariances evolving. You create a big block matrix, and then you'll have this be true for basically D plus D squared different equations. And because their rank condition says that you have rank D, you can just isolate D of these equations and then invert it. You have AB equals A tilde B, but B has an inverse. And then that's how you finally conclude. that yeah, the identifiability claim, because now you isolated what the drift is. Yeah, maybe like this is obviously theoretical, and maybe Jeff's point of just taking, you maybe could just straight up take the expectation and then show some kind of convergence result. But at the end of the day, I don't think, yeah, they're not contradictory. But yeah, you can definitely just get the drift in this way.
What's weird if you start uniform is that it feels like you can just ignore, and you're looking only at identifiability in the limit of data, you can ignore anything that happens after the first step, right? You can just wait for enough sorting points that you've seen the whole space.
Mm.
Yeah, that's why it seems sort of like a trivial question in that setting, because, you know, whatever the function b of x is, as long as it's like smooth or something like that, then if you want b at some x, you just take all the data, you know, around in some ball around that point, and then you see where those points go to at time t plus delta t.
Yeah.
And then that would, you know, take expectation of t, the average of those, and that's b of x.
Yeah.
But if it's all starting from a point, that's not possible, and then I think you have to do something like this. Then you need to make some additional assumptions, like b is linear for it to be.
Yeah, yeah, maybe that's true.
Yeah, it feels like relying on the noise for exploration, like if you wait enough, you see. But then,
Oh, if it's ergodic, I guess you like then even if you just have one starting point, you could get everywhere. I guess that's.
yeah, that's one, so I probably missed that, but what's the assumption of the noise?
Oh, the noise itself is modeled according to Brownian motion. So I'll go back. So, okay, this is additive. How each time step evolves is according to the drift and this guy. So it's going to be a linear function of Brownian motion, and these guys, the increments of Brownian motion are normally distributed. And then, yeah, the other one is a little more complicated because you have to weight the Brownian motion with the contribution from your process itself. Yeah, I won't take too much longer with the theory. So we just showed that in the additive case, a sufficient condition, if you do the rank, then two different observational distributions, if they have the same distribution, will allow you to identify the parameters for the generator. It turns out that this is actually necessary too in this case. What I mean by that is if you have identifiability, then this rank condition must hold in this case. The reason is in this case is because it's really a special situation. If you have a linear additive noise SEM, you'll always have a Gaussian process. The reason you can kind of see it from the solution itself, as long as your starting point is Gaussian, what are you doing here? Like, you're just doing a linear transformation of Gaussians, because DWS, all of these are going to be resulting in independent normal random variables, and you're just adding them and scaling them. So, you know, technically you have to do some kind of limit thing, but it's well known that these guys, like this solutions to this SDE are Gaussian. And what that means is that it's completely determined by statistics. So that's why, yeah, because of that fact, you also show that it's going to be the rank condition will always be true if you have identifiability. I'll briefly just touch on the other case. If you have a multiplicative model, you'll notice that A1, they're going to assume the same rank condition as the previous one, but they will also assume a second rank condition. The reason why they need to assume the second one is, remember, in identifying the diffusion of the linear case with additive noise is really easy. It kind of came from the definition of a generator. You can't do that if it's multiplicative noise. You'll essentially have to do the same process for both recovering the diffusion and also the drift. So you'll need to do the process of actually creating systems of equations with your statistics, and then using a rank condition to show that they're the same. And I won't actually go into how, but it's the same process of equality and distribution gives you same statistics, you generate a linear system, and then you invoke the rank condition. You do this once for the drift coefficient, one for the Gram matrix of the diffusion. And the very last theoretical point is that both of these conditions are, they call general, because according to random matrix theory, if you just select your matrices randomly, then your rank conditions will hold with probability 1, because the set of bad parameters has Lebesgue measure 0. Proofs are pretty involved, so not going to show them, but so that's the theoretical takeaway, which is that for both of these models, there are, with probability 1, if you're choosing your parameters uniformly, then you will be able to identify the generator and hence the post-interventional distribution from just knowing the observational distribution. So 2 observational distributions, if they're the same, will have the same generator.
So I'll briefly discuss their experiments.
The question of the rank conditions.
Yeah. Mhm.
Yeah.
Can I understand that as some kind of like condition that's necessary for exploration or positivity like the one?
What do you mean by positivity?
So essentially, if I don't have this rank condition, is it going to prevent me from exploring enough of the space that I can identify the parameters, or is it just like?
Yeah, basically, yes. I mean, they'll show it in the. I think it's better shown in the experiments, right? Or do you have anything?
No, I think, yeah.
Yeah.
That makes sense.
Yeah, so we'll answer that in the discussion of the experiments. So, the goal of the experiments is to find the relationship between the sample size or the number of trajectories they have and the MSE of parameter estimation of A and G transpose. And they divide it into cases where their theory predicts that the generator should be identifiable versus cases where the generator is not identifiable from the observational distribution. So in all their cases, they only assume a 2-dimensional system. Each trajectory has 50 equally spaced observations on 0, 1, and they repeat their experiment 100 times, each experiment 100 times to get like uncertainty values as well. They generate observations from the ground truth parameters that they're using, simulated ground truth parameters using the Euler-Maruyama method. And they're using MLE for parameter estimation, which requires the transition PDF, which they're also computing using the Euler Maruyama method. So in the additive noise case here, they have 2 examples. One, the first example is the identifiable case, so it satisfies their theorem 3.4. And the second case is unidentifiable. So in the results here in table 1, in an identifiable case, that mean squared error of A is kind of converging to 0 as they increase their number of trajectories. And the same thing with the MSE of G transpose. It's kind of converging to 0. But in the unidentifiable case, you can see that the mean squared error of A doesn't really drop when you add more and more observations. While, yeah, I mean, for the GG transpose case, it kind of increases almost, but it's just, I guess the variance is blowing up or something. Because you can see their uncertainty values here are quite large.
So what makes it stay in the assumption?
So this is, this G matrix doesn't have full rank, I guess. It's, would you say that's the only? Yeah. I don't think they explain explicitly like why it violates it, but they're just developing some example which violates their condition in equation 14, wherever that is. Next, in the multiplicative noise case, they have 3 examples.
It does really have that flavor of the noise, like never pushing you in one of the direction. So there's like one dimension of your space that you just can't observe that. So,
No problem.
Yeah, it's exactly right, because G is like, it's just using one vector basically.
yeah.
In the multiplicative case, they have 3 examples. So 1 is identifiable, and 2 is unidentifiable. It violates the condition A1 and satisfies A2, which is what again?
A1 is the one that's used in both. So A1 is
Both the noise and the drift term, right?
No, like A1 is used across both additive and, like, there's 2 rank conditions. One is used for both multiplicative noise and additive noise. A2 is the one they also need to add for the case of multiplicative noise to get their thing to work.
So their 3rd example is again unidentifiable. It satisfies A1 but violates A2. And here the results. Yeah, here it's tougher to see why it violates these assumptions.
Oh,
I say.
sorry, I'm trying to see something more basic.
Why
Why-
did G1
Why is there a G one?
Oh, it's.
Oh, right, because in the multiplicative case, they have a sum of.
Oh, right, it's like a kind of like combination between the term from X and the.
Well, they just have a sum of multiple matrices here in their multiplicative noise case.
Oh,
So M is 2 in this case, yeah.
Can you say the condition?
Pardon me?
The conditions of the theorem, do you have them?
Yeah, good.
I'm not sure where those are on the slides.
Okay, here, A1 and A2. So, yeah, the first one I kind of went through, like, this is gonna be D squared plus D columns.
Obvious when you show me.
Yeah.
I guess X0 is like an eigen.
X0 is just the initial condition.
Oh.
It's still, I mean, they. Okay, wait, they have,
Yeah, but in 2x2 case, X0.
Oh, wait, actually, it
is
might-
an eigen.
might not be the same, actually. Yeah. So this is the one, I might have gotten it wrong, like, they might not have reused this in both. But yeah, it might be actually 3 different rank conditions that are being used in, one's being used for additive, 2 are being used for multiplicative, but. It's just whatever they need to get their system to work.
Yeah, I mean, I remember somewhere in the paper, they said that A1 is, that it's only considering the drift term and the A2 should consider both somehow, but it's not clear to me from this,
Yeah.
how that's true.
Oh, it is, there's a
Just
definition
A.
here. Script A. The script A and there's.
Oh, right,
A.
yeah.
So that's,
So A1 just characterizes some condition on the drift term, A2 characterizes kind of the relationship, I guess, so. Or maybe it's just a defeat. I think it's both. Okay. So because they only proved sufficiency in the multiplicative case, you can see that even in the unidentifiable cases, in these examples, the MSE for A and MSE for G is decreasing to 0, but it kind of starts at a higher point when you only have 10 trajectories, and it kind of decreases a bit more slowly. For case 2, it's kind of again the same thing. It's still, the MSE is still decreasing, but the MSE for G is kind of starts huge and then it very slowly decreases they say it's going to zero, but you know, it's kind of unclear if it'll converge at this point. So, yeah,
Miss something in the experiment, how they find the matrix, for example, A,
mhm.
then they calculate the loss. What's the cost of finding matrix A?
So, these A's are just the ground truth values that they're using for their experiments, but in practice, what they're doing is generating, you know, 10 trajectories and then using maximum likelihood estimation using like this Euler scheme. I mean, they didn't really explain this very clearly, honestly. It's mostly in the appendix, but yeah, they're just using MLE to estimate the parameters.
Wait for me, because that Euler something is for simulation.
Yes, but
Here,
but yeah, but they also, to get the parameter estimation, they say they need the transition PDF, and apparently you get that from the Euler method as well. That's what they said. So,
Transition between.
transition between the values of X over time, yeah.
that's the thing that we get from optimal transfer.
I don't think so, but. We should make sure that.
So from this paper, I'd say there's 3 main points to conclude and summarize. It presents conditions under which the generator and hence the post-intervention distribution is identifiable from the observational distribution. They show that the generator of the linear SDE with additive noise or multiplicative noise is identifiable from an arbitrary observational distribution with probability 1 if your SDE parameters are sampled uniformly. And the primary method for recovering the generator's parameters is by kind of creating a corresponding system of equations and using the equality of statistics, mean and variance, covariance, I guess, across all times and increments, and the rank condition of this system should be invertible. If I'm being honest, I'd say that this paper raised more questions than answers for me. So some kind of critiques or questions that we had that maybe we can discuss is that they only had like 5 sample matrices in their experiments, and I'd be curious to see them just generate hundreds of random matrices and see if the error kind of decreases nicely as they add more and more trajectories. I'd also like to see experiments where they add like a small perturbation to a non-identifiable system to see if the errors nicely converge and start low, because it could be, I mean, it could be like the faithfulness case where you have probability 1 that the graph is faithful, but you know, you're always very close to something that's not faithful, right? So that could maybe screw up the estimation somehow. I think Vince wants to see if their proof techniques can be adapted to nonlinear SDEs. And with regards to the equally spaced points, so all the experiments considered equally spaced points. So we're kind of wondering if the theorems still hold for normal time series and if they really need that their kind of continuous SD system. And if their theorems don't hold, then why not? And also, we'd like to see, you know, if we only have 1 trajectory and the process is not ergodic, can we get somewhat of a good estimation of the parameters as well? That's it. Thanks. Questions?
Yeah, I guess I'd be curious to see the details of the estimation procedure. But
Okay.
it's in the appendix, that's strange. Maybe it's just really easy.
I don't think it's really even in the appendix. They kind of just say they did MLE and
It's probably Gauss, they assume it's probably a Gaussian process, and then that's probably it. I think it's a well-known estimation. MLE.
Okay.
I also want to check if they're assuming at the same starting point, because I don't remember reading that anywhere, but to check. But people can ask questions as I'm doing that.
I have a question for the paper by. So I remember, you kind of briefly said that, mentioned that there's no, you can't. Identify the parameters, and that's why they weren't considering the SDM formulation. Like they were considering the interventional distribution. But not,
Yes, they are starting.
they didn't care which variables the derivative of X had depended. Like they didn't construct the graph from that. Because
Oh, yeah.
it wasn't.
So because sometimes we're getting, so they had this example of two SDEs, which had the same post-interventional distribution. But we're getting two different graphs, we're coming from two different graphs.
Mhm.
So they were saying that they are causally equivalent because they have like the same post-interventional distributions. But this means the graphs are not good things to look at to infer this causal relationship. Doesn't like,
So there were two different basically formulas that give the same.
yes, so two different formulas that were giving two different graphs, but the same post-interventional.
So what about the actual observation? Is also the same? Yeah.
I think observation and distribution would be different, right? Yeah.
No, I wonder if it's just the same thing as the sigma transpose being equal to some other one. I don't know if it's the same.
But you only, I would create the graph from the grid.
Yeah. But maybe something else is going on. It's just a guess.
Yeah, that's kind of one of the most interesting parts is like you can't estimate parameters, but you can get the post interventions, which is kind of rare, right?
Yeah, so they had the same. The same observations, about two different graphs.
What kind of?
This one here, they have this matrix A, and then they somehow construct another matrix, A tilde, where A transpose is equal to A tilde transpose, so the distributions are, the observational distributions are the same. But then they argue that the graphs could be different.
Oh, but that is a distribution.
Okay, so it's what, yeah, why would I change the graph?
Did they not have a grid graph? There was nothing like this plus.
I don't know, yeah, it's just, it's there. They don't have
Oh.
VT term here,
Oh, but did they have an agenda?
they have in general.
That wouldn't create the graph from that. There's also a kind of.
I mean, in their definition, this graph, which they call signature, is like 1 points to 2 if one appears anywhere on the right-hand side of the equation that it points to.
That
So, yeah, they don't say where.
Including the diffusion.
Because if you want like additive noise. So that the diffusion doesn't have any. estimate,
Yeah.
Then.
Because the general SDE in this paper is just like the noise is just a semi-martingale and it can be anything, while in this one, they have T and WT, where WT is apparently Brownian function, so.
Yeah.
It's a little more restricted.
Yeah, I just want to emphasize this last point, like there was a question about, if they're assuming the same starting point, and in the experiments they are, so in each case, they have the same starting point for all trajectories.
Yeah, I think that they define equality and distribution as, yeah, like you need to have the same starting point in order to be equal distribution. That's how they define it, pretty sure.
But they don't have to define, like, the starting point can be arbitrary. It's not like they always set it to 0 or something, so.
Yeah, but I think they would say that it's no longer equal distribution.
Yeah, so I guess it'd be interesting to know what is the largest class. And
Yeah.
I don't know if it's known or, I guess they